An explicit rule gives a sub n as a function of the term's position number n in the sequence. That's what we've been dealing with so far in this chapter. Explicit rules allow us to give you an n value, you plug it in, and you can find any output of the sequence. A recursive rule, on the other hand, gives the beginning term or terms of a sequence and then a recursive equation that tells how a sub n is related to one or more preceding terms. So we're going to write the first 6 terms of the sequence. This is a recursive rule. They're telling you to take the previous term, n minus 1. If we're on the nth term, the one before that would be n minus 1. So we're going to take that previous term and add 4 to it. So they have to define at least one term for you in order for you to even be able to use this rule, because it says to take the previous term and add 4 to find the next one. So if we want a sub 1 is equal to a sub 1 minus 1 plus 4, which means a sub 0 plus 4, and a sub 0 is 1, so 1 plus 4 gives us 5. The second term, a sub 2 minus 1 plus 4, so that means to take the first term plus 4, and the first term was 5, so 5 plus 4 gives us 9. A sub 3 means a sub 3 minus 1 plus 4, so a sub 2 plus 4, and the second term was 9, so 9 plus 4 equals 13. So you can see we just keep adding 4 to the previous term. So the first 6 terms of this sequence are 5, 9, 13, 17, 21, and 25. Example 2. This time we have a geometric. We're going to take our previous term and multiply it by 3. This one was arithmetic. We just keep adding 4. But this time we're going to multiply by 3. So it's a geometric. They define the first term. So we can start with a sub 2. So a sub n equals 3 times a sub n minus 1. So if we want a sub 2, that means 3 times a sub 1. And a sub 1 was 1, so 3 times 1 gives us 3. If we want a sub 3, it's 3 times a sub 3 minus 1, which would be a sub 2. So 3 times the second term gives us 9. A sub 4, 3 times the third term, a sub 5, 3 times the fourth term, and a sub 6, 3 times the fifth term. So the first 6 terms of this sequence are 1, 3, 9, 27, 81, and 243. So let's fill in our key concept box. Recursive equations for arithmetic and geometric sequences. So in general, for an arithmetic sequence, a sub n is going to equal the previous term, so a sub n minus 1 plus the common difference. And you have to make sure you define at least one term. So you have to tell your audience the first term is this, or the zero term is this. Otherwise, they don't have anywhere to start and they can't use your formula. For a geometric sequence, the general rule is a sub n equals your common ratio times the previous term. And again, you have to define at least one term so that people know where to start and can actually apply your rule. Write a recursive rule for the sequence. Number 3, 140, 16, 32 over 5, 32 over 5, and 64 over 25. So if we zero in on these two, first of all, I know it's not arithmetic because 100 take away 60 gives you 40, but 40 take away 60 would give you negative 20, which is not 16. So arithmetic was out right away. I'm thinking it's geometric. It's going to be easiest to see my common ratio here on these last two fractions. 32 times 2 is 64, and 5 times 5 is 25, which tells me my common ratio is 2/5. And so to check it, if I take 100, which is really 100 over 1, times 2/5, I get 200 divided by 5, which equals 40. So I have the correct common ratio, so my rule, a sub n will equal 2/5 times a sub n minus 1, given that a sub 1 equals 100. Okay, so keep in mind that not everything is an arithmetic or geometric sequence. Sometimes we just have a different type of pattern. So let's take a look at this next one and try and figure it out. So if I test to see if it's arithmetic, well, I'd have to add 18 to go from negative 10 to positive 8, but then I'm only adding 10, and then I'm adding negative 8, and then negative 18. So it's definitely not arithmetic. I'm not adding the same thing every time. It's also not geometric. I know that because the signs, the negative becomes positive, which would mean I'd have to multiply by a negative, but then it stays positive, and a positive times a negative would get me a negative. So this is not arithmetic or geometric. What I can see, though, well, let's try and relate the terms back to one another. So I noticed that these two, if I do 8 and I take away negative 10, I'm going to get 18. And if I take 18, take away 8, I get 10. 10 take away 18 is negative 8. Negative 8 take away 10 is negative 18, and so on. So the relationship here, if I want a sub n, I gotta take the term before it and subtract from that the term before that one. So for example, to get 18, I have to take the one before it, which is 8, and subtract from it the one before that, which is negative 10. 8 minus negative 10 is 8 plus 10, which is 18. If I want to get 10, I have to take the one before it, 18, subtract 8 from it, which is 10. So I need to define two terms for this one because I need two terms to make my pattern work. So the first term is negative 10. The second term is 8. And to check to see that it works, a sub 3, well, we take the term before that and subtract the term 2 back from that. So that means take a sub 2 minus a sub 1. A sub 2 is 8 minus negative 10. And you get 18, which checks. So let's try and figure out the pattern on this next one. So if I'm looking at it, I see right away it's not geometric because 1 times a half gives me a half, but a half times a half would be 1/4, which is not 1/6. It's also not arithmetic because 1 take away a half will give you a half, but half take away a half would be 0 and not 1/6. So there's got to be some other special type of relationship here. So I notice that I do 1 times to get this term, and then I do 1/2 times 1/3 to get the term after that, and then I do the 1/6 times 1/4 to get the next one, and then if I do 1/24 times 1/5 I get the 1/20. So my denominator is being multiplied by 2, then 3, then 4, then 5, which corresponds to the n value. So a sub n will equal 1 over n, that's how I get the n to the denominator, times the previous term. And I have to define at least one term, so the first term is 1. Here's our check. So if I want a sub 2, I take 1 over 2 times the previous term, which would be a sub 1, and 1 over 2 times 1 gives me the 1/2. You could check for a sub 3, so a sub 3 would equal 1 over 3 times a sub 3 minus 1, or 1 over 3 times a sub 2, 1/3 times 1/2 gets you the 1/6. So with these, it takes patience and really examining things on this problem. Your denominators were being changed and they were being multiplied by 2, by 3, by 4, by 5, by 6, which happens to be the n value, the number of the term that you're on. So that's how we could figure out that you're multiplying by 1 over n, and you just keep taking your previous term and multiplying by 1 over n. Let's take a look at number 6. So 8, 28, 48, 68, 88, we can see we're adding 20. So your common difference is 20. So a sub n will equal your previous term plus 20, and we have to make sure we define at least one term. So a sub 1 equals 8. Alright, so iterating functions. Iteration involves the repeated composition of a function f with itself. So recall back a few units ago when we talked about composition of functions, where you take one function and put it inside of another function as the input. Well, we're going to repeatedly do that. The result of one iteration is f of x. So we did some examples like that a few chapters ago. But now we're going to see what happens when we keep going. So if we iterate 2 times, we'd get f of x. You can use iteration to generate a sequence recursively. So you begin with the initial value x sub 0. You let your first term equal f of x sub 0. You let your second term equal f of x sub 1, which equals f of x sub 0, and so on. So you're going to find the first three iterates of the function f of x equals negative 3x plus 1 for initial value of x sub 0 equals negative 2. So basically what you're going to keep doing is taking the number you get and plugging it back into this function. So you're going to take negative 3 times the previous term, which in this case was negative 2, and then you're going to add 1. Negative 3 times negative 2 is 6, plus 1 is 7. So that's your first iteration. X sub 1 equals 7. So now we're going to take that and plug that into the function. So negative 3 times 7 plus 1 gives us negative 21 plus 1, which is negative 20. So that's your second iteration. We're going to take that and plug that in to find our third iteration. So the first three iterates of this function are 7, -20, and 61. And if they wanted you to keep going, you would just take 61, plug it into your function, get an answer, take that answer, plug it back in. That's all iteration means, is you take your starting value, plug it into the function, get an answer, and then take that answer, plug it back into the function, get another answer, plug that back in, and so on. You just keep composing the function with itself. So iterations is an application of recursive functions. Recursive functions sometimes are easier. It's an easier way to describe some functions. For example, number 5 that we did on this page. But they can be more challenging if you need the 100th term and they've only told you the first term, because you'd have to sit there and write out all 100 terms. If you have a problem like that where you're trying to find one specific value, the explicit rules we've been looking at are more helpful. But you need to know both, so practice, practice, practice.